Good afternoon, everybody. We'll just wait another couple of minutes, few seconds. Okay, so good afternoon, everybody. Welcome to the Supergen Offshore Renewable Energy Hub webinar series, and thank you very much for joining us today. My name's Deborah Greaves. I'm based at the University of Plymouth, and I'm the director for the Supergen Offshore Renewable Energy Hub. And we run these every 2 months approximately, and we're very keen to share the research across the offshore renewable energy area, and we're always looking for volunteers to share their research. So if you're interested in giving one of the webinars, then please do get in touch. So we're joined today. We've got two really interesting webinars which have been offered from Cardiff University and University of Dundee. So thank you very much for joining us, and we're going to kick off straight away. So we'll start off with Dr. Aristos Christou, who is a research associate in offshore and coastal engineering based at Cardiff University. And Aristos is going to talk to us about the advantages of numerical simulations of floating structures in offshore environments. And Aristos, if you'd like to share your screen when you're ready, and we shall start straight away. So we're going to run each. We've got two presentations. We'll listen to each one and take questions after each of the presentations. Very good.
So,
okay.
Yep.
Thank you, Aristos. Over to you.
So thank you. First of all, I would like to thank you, everybody, for joining the webinar and for having me with you to be able to present. So my name is Aristos Christou. I'm a research fellow at Cardiff University with Dr. Ziwazi, and I graduated from UCL, where I did my PhD in CFD and fluid mechanics in coastal and offshore engineering. So today, I'm going to talk about investigating wave structure interactions and fluid structure interactions in offshore environments using the method of large-eddy simulation. So I will cover several steps of the process, from developing the numerical wave tank, validating the code, and also applying the LES numerical wave tank to realistic offshore environments applications. So the sorry, got here. Okay. So I'll go through some introduction, then, as I said, roughly describe the numerical background, and then give some example of wave structure interactions. First of all, fixed structures, which was the process developing the numerical wave tank, as, for example, a 3D solitary wave over a thin flat plate, or sinusoidal waves on a submerged step, and then a more realistic case of focus waves interacting with piston cylinders in depth-varying shear currents. And then finally going to floating structures, where we further accommodate a new toolbox on the numerical wave tank to simulate floating structures, as, for example, decaying motion of a sphere or the impact of a triangular wedge, and then floating box interacting with waves in the numerical flume. First of all, and I'm sure as we all know, there's a big potential in offshore energy exploitation in order to reach national and international targets to reduce the climate change. And obviously nowadays floating structures seems to be much more suitable when it comes to deep water or rough seabed compared to fixed solid structures. And additionally, the improvement in computing power and the reduced Computational cost boosted the development of numerical methods. Several approaches exist in the literature. For example, velocity potential or smooth particle hydrodynamics or CFD, wherein CFD is what we call the Navier-Stokes based simulations. And the big question is why LES? Obviously, many applications or many numerical wavetimes with different approaches can generate quite accurate results. But when it comes to strong wave breaking or flow separation or currents interacting with waves and all that stuff, then LES with a sufficient grid resolution can be a powerful tool, especially understanding the local flow hydrodynamics and the physics involved, which will end up giving a more efficient design for coastal protection or devices for offshore energy exploitation, such as offshore wind turbines, oscillating water columns, etc. In this code, in this numerical wavetime, we use the Navier-Stokes equations, the spatial filter, viscous and steady Navier-Stokes equation, where partial derivatives are decomposed based on finite difference scheme on a staggered Cartesian uniform grid, and then Ranke-Gouda is used to go and do the time advancement and calculate the velocity and pressure field in each time step. Most important part of this code is the large-eddy simulation methodology. And as we can see from figure 1, we have the direct resolved velocity tensor from an area or for large flow structures which are greater than the grid size usually, and it's similar to the DNS, where flow structures smaller than the grid size and their dissipative effect is calculated or actually modeled using a subgrid scale model. In this case, the wall adapting local eddy viscosity, where we use information from the resolved velocity of the large scale to calculate the eddy viscosity and sum it to the fluid kinematic viscosity. The advantage of this subgrid scale model in the wave is the fact that near viscous layer and near walls, the eddy viscosity is almost zero, and therefore we do not have to add additional damping functions near the walls, as for example, the Smagorinsky subgrid scale model. Equally important is the fluid structure interaction and the way we generate solid boundaries. In this case, we're using the image boundary method, where if we have a solid structure inside the numerical wave tank, we use Lagrangian markers, as you can see from here, figure 2, the cross here, the red cross here, where Lagrangian markers form the geometry, the solid geometry of the structure, and then velocities of the fluid cells are interpolated to the location of the Lagrangian marker to calculate a force to enforce a no-slip boundary condition. This is the case when we have static and fixed structure. When it comes to moving structures, then the surrounding pressure and shear stress are recorded near the structure, interpolated around the structure, and then integrated to calculate the force and the moment. And here's solve the equation of motion of a rigid body to calculate the acceleration and therefore calculate the new location of the structure, where we update the displacement or the new location of the Lagrangian marker, and then we enforce the no-slip condition. And therefore, every time step, we have a solid structure moving around the numerical flume and also enforcing the no-slip condition around the structure. Obviously, when it comes to numerical wavetime, we have free surface flows and multi-phase flows. In this case, we're using the level set method, which is similar to VOV. We have a sign distance function called phi, where cells with negative phi values are cells in the air and positive phi values are cells in the water, and zero values form the interface between the two. And then we just solve a pure advection equation using velocity field from previous time steps to calculate the new location of the water surface. Figure 4 here shows a multi-phase simulation employed with the surface tension and a single rising bubble in viscous fluid, and we can see how the water surface changes in shape and location. And then the numerical wave type. We had to introduce a new toolbox to generate and absorb waves. Here we generate waves based on analytical solutions of available wave theories, for example, up to fifth order, nonlinear stokes, sinusoidal waves, solitary or focused waves, or even we can input kinematics from previously experiments conducted, and if we want to exactly reproduce some experiments. In this case, equation 13 to 15, for example, shows the solutions for Stokes waves, second order Stokes waves. Going further, we can see how we absorb the waves. Equally important, we don't want reflected waves to move back to the water plume and back to the interacting with incoming waves. Therefore, we're using the relaxation method. We're using equations 16 and 17. We use a gamma function here to gradually absorb the waves by setting the velocities and the water surface to still water conditions using various constant and polynomials. We can see in figure 7 here how the water surface looks like after several wave periods of generating waves. We have the waves coming from an inlet and absorbed here at the very end. And then we have some screenshots of the water surface in space and how the time step affect the actual generation of the waves. So now into the more interesting stuff and applications. Here I wanted to put this case to make the point of the three-dimensionality. Here we have a pure thin plate very close to the water surface and a solitary wave propagating over. This is roughly a 2D case. So we can see that we have the plate extended through the side walls of the domain. Obviously, we validate the wave elevations in figure 10 and the forces in figure 11 with additional or with relevant experimental measurements. Results are pretty good. But then we wanted to see what it looks like if we include the three-dimensionality. And therefore, we went to next step. And what we did is that we increased the width of the domain. And now we have a square plate, not extending through the side walls. And we noticed a big jump on the water surface over the plate, which was due to the ability of the flow to come from the lower side to the upper side of the plate through the lateral edges, the side walls, let's say, of the plate, generating some nice eddies here, interacting with the structure and the water surface. And then figure 13, we can see how indeed the wave or the water surface over the plate increases and then breaks further downstream, generating some energetic eddies on the leading and trailing edge of the plate. Then similar to this one, we have sinusoidal waves in shallow water depth, long waves interacting with a submerged fixed step again, where in here we tested two cases, two heights of the step, one being half the water depth and the other one being very close to the water surface. And we can see the differences on the next slide. Again, we want to first validate the code and then extend the results and apply the large-eddy simulations to visualize the local hydrodynamics. Therefore, we can see wave elevations matching well with the experiments and also the local flow field from PIV measurements from previous conducted experiments by Zhang et al. And now we can see these two videos here, which on the central panel, we've got the smaller step, half the water depth, and on the right panel, we can see the steeper structure. We can see the same wave conditions, how the wave breaks, and how eddies are formed at the leading and trailing edge. And the important part here is that, and it's really crucial when it comes to this kind of simulations, even though the structure is a 2D structure, by 2D, I mean extending from sidewall to sidewall, we can see that three-dimensionality exists. And we can see how the eddy, the rotational flow structure are separated from each other, generating random eddies moving through stemwise and all the directions, and how the breaking wave interacts with the flow structures itself. finally, when it comes to fixed structures, we've tested focus waves interacting with shear currents or depth varying currents. So we have waves, and then we have underground currents with maximum velocity on the water surface and zero on the flow bed in two directions. The one case was currents following the shear current, the waves, and then on the other hand, we have the current going in the opposite direction. I don't want to spend a lot of time here, but worth noting, if we have only the current, we can see the horseshoe vortex here and the turbulent current behind the cylinder, and how these generate or affect the flow bed wall shear stress. This is a wall shear stress on the flow bed without waves. And then the dark red spots here is how the waves, the focus waves, affect the wall shear stress. And it's worth noting that the area enclosed the horseshoe vortex stays unaffected, whereas area outside the turbulent wave and the horseshoe vortex it's affected quite a lot from a wave-induced flow field. Another animation here. And then when it comes to fluid structure interaction and the floating structures, again, we have to develop the code further to accommodate moving structures. Again, here, we don't specify the motion of any structure. We calculate the flow peak, velocities, pressures, and then we calculate the new location of the structure. So we use solid benchmark cases to examine the accuracy of the code in such applications. For example, here we reproduce experiments of solid sphere oscillating in still water conditions from an initial height. Here we present results from the steepest case, or the case with a higher level of initial elevation. We can see the vector field, velocity vector field during elevation, but more importantly, we can see how the solid, the sphere, and the water surface interact. And we can see that ring-type waves propagating from the outside, and figure 32 capture this elevation in time through 3 wave props, and results are compared with experiments, again, with some decent validation. And this is a really good advantage of this code, is we can calculate and visualize the flow field, the water surface elevation, and also the location of the structure. Then we extend the simulation to impact of wedges of really heavy structures with high pressure impacts. We can see here how that we recorded the vertical location and the vertical velocity with decent results compared to the experiments, and then screenshots of the water surface and how these water surface looks like during and after the impact. Again, using the level set method for the water surface. And then recently, we include the rolling motion of the structure. We want to do a 6 degrees of freedom numerical wave tank. So in this case, we have the damping roll motion of a rectangular box, where in still water level, we give an initial angle. In this case, it was 15 degrees, and then we leave it rotate. And we have the damping motion in the rolling damping motion of the rectangular box. Figure 36 here, we can see the motion compared with the experiments with quite decent results. And then, again, we can visualize the turbulent or the rotational flow structures in terms of wide vorticity and how it looks like near the corners and around the step or around the structure, both in water and air. And then finally, fluid structure interaction in terms of a floating box interacting with waves in 2 cases, shallow waves or relatively small waves, and then some steep waves, case 1 and case 2. Figure 39 shows some validations of the vertical and horizontal motion of the same problem, which results are compared with the experiments previously conducted by Renby et al. And then figure 40, we did some comparisons between screenshots of images from the experiment, compare side to side with the simulation and the LES, and we can see both the water surface and the location, angle, and horizontal and vertical location of the box being quite similar with the experiments, which is quite interesting, being able to reproduce time-consuming or expensive experiments in a numerical simulation. And on the left panel, we can see some rotational flow structures in terms of the Q criterion near the floating box, and how these eddies are formed in one time step and then moving with the box and the wave. I didn't start with I don't know if I took more time and if I have to terminate now, but summary, the numerical wave tank based on large-eddy simulations has been developed and validated in ballistic applications. Important parameter here is that with sufficient grid resolution, then LES can really predict the local flow hydrodynamics and be used as a tool in the design process. Three-dimensionality is crucial, even though some cases seems to be two-dimensional. Three-dimensionality indeed exists. And then large-eddy simulations with these specific sub-models, level set method, IBM, uniform grid, can be used to generate a complicated fluid structure interaction model. Some ongoing projects, we've got results from LES sharing to machine learning codes to estimate the flow field and Reynolds stresses, which is something really interesting nowadays. And then some floating breakwaters to be retrofitted with tidal turbines. And also, thanks to the project or the fund that you get the funded project by Archer 2, the current numerical wave tank will be available and open source, hopefully sometime near the future or soon. And then we could all use and start some simulations. So thank you very much for the attention, and hopefully you have some questions that I'll be glad to answer.
Okay, thank you very much, Aristos. That's really very interesting, and some really nice results there, and some lovely videos and images. So I'm going to ask people to, if you've got a question, please would you use the raise hand function, and then you can ask your question. You could also put questions into the chat if you prefer, but seeing as we're all in the room together, it'd be good to hear your questions in the room. So I'd like to ask a first question, if that's okay, to kick things off. And I think all of the simulations you've shown us are using LES, is that right? Yeah. So my question is, have you tried any other turbulence models, or have you looked to see what how different that would be from a laminar simulation? In particular, I'm thinking about your case where you have the 2D block with some really strongly 3D behavior.
Yeah, so we didn't actually use, so the code is based on LES. We obviously have other models like Smagorinsky, but whale model seems to work better. But when it comes to other approaches, like for example, runs or a different whole approach, we didn't run it, but because in these published studies where they did experiments, usually they have run either open form or runs. We did make the comparisons. Most of the cases are equally good, both. That's why I said in the very beginning, there are specific cases where the LES might be better. As for example, in the 2D block and the waves over the block, in the step where the height is half the water depth and not very close to the water surface, comparisons, especially of the wave elevations and vorticity magnitude, it's very similar with the code they used. I think it was runs in that paper, to be honest. But then when it comes to the steeper case, the 0.75, the really steep block, a massive block. They didn't, or they are not available simulations on that paper, at least on that publication. And therefore, it will be a good idea to run some maybe open form or something else in terms of runs or SPH or a different approach to see the differences. But for example, in the plate case, where we did compare with another approach published in that paper with that plate, we saw that the flow or the wave after the plate, downstream from the plate, we really match the peak of the wave. Whereas in that paper, the peak was overestimated, which have to do with the dissipation and of the wave during the motion over the plate. But yeah, most of the cases, someone could say that LES is, or in some cases, LES might be overrated or something like that. But in the case of the current and the focus waves, or really wave breaking or steep motions or floating structures, the large-eddy simulations, I think, is efficient and computationally cost-wise, and also in terms of accuracy.
Okay, thank you. Thank you very much. Okay, I'm just looking to see if there are any other questions from in the room. I've got a whole stack I could ask, but just giving anyone else a chance. Yes, Hannah, you've got your hand up. Yeah.
Hi, yeah, great presentation, Aristos.
Thank you.
I really enjoyed all your videos and all your different comparisons that you've made. I was just wondering, towards the end, you were talking about the floating structure within the waves, and you had the box that was moving. Have you looked at mooring systems and mooring cables and those connections to those structures and how they interact? Is that something that's a future work or something you've already looked at?
I think that's the way forward. And eventually this is what, I mean, at the end of the day, you care about the design of the mooring lines or the pressures and forces acting on the mooring lines. At the time being, we're using experiments where we have the structure free to move in any direction, as experiments we did with the floating box. Not we did, we reproduced. It was done by another group. To make sure, first of all, it's a step-by-step process that we can capture the full motion of the structure, because obviously it's not prescribed, therefore it's highly affected by the grid resolution, by the water surface. If you calculate the water surface correct, the pressure, and so on. And then I guess it's a step forward.
Okay, thank you.
Okay, thank you very much. Tim?
Hi there. Sorry, just too many buttons. All two. That's too many for me. Yeah, thanks for the presentation, Aristos. All interesting stuff. So I guess mine about the surface method, the level set method that you have. You have a number of problems there, like the wedge entry and the breaking wave around a vertical cylinder, where you might expect to observe in the experiments jets or separation of the surface and formation of droplets. So does the level set method currently allow you to capture that breaking off of fluid bundles and the re-immersion, I suppose, of those fluid droplets back into the fluid? And if not, are you looking at any developments of the level set to capture the breakdown of the surface?
So again, a really good question. It's always the case with the level set method. Obviously, we had to introduce the surface tension, first of all, to make it able to do the wave breaking and all that stuff. But again, I think maybe the main drawback of level set method, it's quite dissipative in terms of, like, for example, if we use on the solitary wave propagating inside the flume with the level set method, we can see some damping, we might be not expected. And therefore, if you go really fine in grid resolution, we were able to, with the surface tension, to capture some breaking, wave breaking, and the droplets and results was accurate compared to screenshots from the experiments. But when it comes to droplets and going from droplets back to changing phase, that might be an issue, or we have to go really fine. So what we did, instead of further developing, which again I think it's worth studying and doing, we use sometimes, or in one case, for example, we use kinematics from Lagrangian model, for example, and we had a really small domain with really fine resolution to capture only the braking. Let's say it was plunging braking, for example, to do that. So we had to go really fine. Doing development in the level set method for this large scale simulation we're doing, we haven't yet, but I think it's a good way forward for the level set method. I don't know about the hybrid scenarios of level set method being hybrid with other water surface capturing techniques, if that helps, but I didn't look into that, to be honest.
Okay, thank you. Thank you very much for that. And yes, I think you mentioned at the end of your slides that machine learning and other approaches are on the horizon as well to bring into this type of work. But really nice presentation. Thank you very much, Aristos. You mentioned using Archer 2. Are you doing that through the HEC WSI by any chance? If not,
what?
Sorry, there is a high-end computing consortium, a HEC, in wave structure interaction that we run. And just a note to everybody, really, that if you're doing this type of simulation and you want to have access to Archer 2, then you can do it very easily by going through the HEC WSI. I'll put a link into the chat.
No, that was it's a project funded for 2 years from Archer to make the code open source. So I don't know if it's from the same source.
Okay. Probably an ECSE one. Yeah. I'll put a link into the chat, and you might like to have a look at that website as well about the HEC. Good. Okay, but I think we ought to move on to the next presenter because I don't want to run out of time. So thank you very much again, Aristos, and also everybody for the questions. We'll say thank you very much to you, and we'll move over to our next presenter. So we have Dr. Pengpeng He, who's a lecturer of geotechnical engineering. So we're going subsea now, or subground, at the University of Dundee. And Pengpeng is going to talk to us about the pull-out capacity of offshore anchors in spatially variable soil. So over to you, Pengpeng, if you'd like to share your screen.
Yep. Thank you, Deborah. I'm going to share. 1 second. Okay. Hopefully you can see my slide.
Yep. Yes, that's perfect. Go ahead.
All right. Thank you, Deborah. Thank you, everyone, for joining us, especially on Friday. So I'm Pengpeng He. I'm a lecturer based in Dundee, University of Dundee. Joined the university 2 years ago, I think just exact 2 years today. And I'm a civil engineering, specifically focusing on geotechnical engineering. I don't know how many civil people here. I went to the Supergen annual assemble a couple of months ago in Plymouth. I didn't see too many geo people here, so I thought probably this is a good chance for me to show something about the geo. Just a very quick overview of University of Dundee geotechnical engineering. So currently we have a beam centrifuge, that's only one in Scotland, many in Cardiff using that. And we also have earthquake shaking equipment and also bespoke soil characterization equipment. And our current interest is more about floating wind anchoring system. Of course, we are also doing some onshore structures. Some people are doing slope, and also nature-based solutions like a interaction between the soil and the vegetation for slopes as well. And those are some key projects we had recent years. So this is just a very quick overview of UOD geotech. And some information about my research interest is mainly about offshore geotechniques and the floating anchors, and also the offshore set investigation, set characterization. The other part is about probabilistic analysis and also risk assessment of geotechnical structures. I also did something about code calibration for the design standards. And I'm also doing something about machine learning, trying to apply machine learning in offshore geotechs. And this is my personal page. It's my Google Scholar. This is my GitHub. If you're interested, just scan the QR code. I think this is easier than the link. So today, I'm going to talk about the anchor pull-out capacity, but not in homogeneous uniform soil. It's in the spatial variable soil. So first, I'm going to give some backgrounds, very, very broad backgrounds to lay persons, not just geo person. So the big background is about floating offshore wind turbines. Those are some tabs here. I think many people are familiar with this. And this is very, very multidisciplinary. And our current focus is about anchor. It's about the seabed part. So I put some commonly used FOW anchor here. One is the gravity. It's a gravity tab. The other one is a Pell tab. Third one, the plate tab. So these are some very, very simplet version. And so the first one, the gravity tab is very, very heavy. It's not very cost effective. So it's mainly about the pre-cast concrete and some ballast. So generally the mooring lines will lift the anchor. So it's pretty heavy. And sometimes you have to provide horizontal or just an inclined load, like the second one, the third one here. So we'll put some ribs or grillage, penetrate the seabed, then we can have some soil reactions horizontally. So the second one is very, very commonly used. It's a Pell tab. So there are two tabs here. One is very, very slender. The other one is shorter, so it's more rigid. And for vertical loading, the resistance mainly comes from the interaction, the shaft friction, the interaction between the Pell and the soil. And when it comes to the horizontal inclined load, the soil reaction, the static reaction will provide the resistance as well, like this one. So those are the failure mechanism. And the third one is about the plate tab anchor. Generally, we have those two tabs. One is the drag embedment anchor. So this is very straightforward. We just put the anchor onto the seabed and we apply toe force, and the anchor will follow the trajectory like this one, and will go deeply somewhere, reaching the ultimate penetration depth, and then it can provide horizontal and also vertical resistance. And the other one is a vertical loaded anchor. We also call it VLA. So it's a plate anchor. We use the sectional driven Pell to install it to some depths, and then we can, like the DEA, like that one, we can just drag it, and you will see the keying precise, like this one, and also we'll get some depth loss. It can provide a vertical loading. This is the failure mechanism for shallow plate anchor. The failure mechanism will reach to the seabed, as you can see here. The second one is the deeply embedded anchor. The failure mechanism won't touch the seabed. It's very, very local. So in this presentation, I'm going to show how to predict the pull-out capacity of this vertical load of this VLA plate anchor, but in the spatial variable soil. So this is the traditional prediction equation. So it's the anchor pull-out capacity equation for strip anchor. So we can just use 2D. And this is for homogeneous soil, which means soil property everywhere they're the same, they are uniform. So generally in geotechnical engineering, we have predictions for clay and sand separately because they have very, very different characterization. So for clay, for shallowly embedded anchor, we have the NC, which is a non-dimensional pull-out capacity factor, is a function of the soil property. The gamma parameter is the soil unit weight, and SU is undrained shear strength. Is the shear strength parameter of the soil of clay. And for deeply embedded anchor, which is the second figure, you can see that it's a constant because once you go deeper, it doesn't affect because failure mechanism is very local. It doesn't, the seabed surface doesn't affect anymore. And we can also give the very, very similar NC, the pull-out capacity factor for like the linear increasing soil strength with depth. It's not just uniform. This is also similar equation. We just put another equation, which is a function of the gradient. And for sand, it's simpler. We don't really differentiate shallow or deep. We just have a single equation. The N gamma is also the same as NC. It's a pull-out capacity factor, which is non-dimensional. It's a function of the phi. Phi is the friction angle of the sand. So this is quite simple. And but what about the real seabed? So in the traditional prediction equation, we just assume that the soil is uniform. The soil property is the same everywhere, so it's spatially homogeneous. But the real seabed, for example, this one, this is a CPT. It's kind of a field test approach. So this QC is a CPT test result, and the resistance result, you can see that it's almost linearly increasing from the seabed, but there are large variation, especially with increasing the depth. And the other one is undrained shear strength, is SU, we just mentioned. So it's also linear, almost linear increasing, but have a very wide bounds, lower and upper bounds. So it's sometimes in practice, it's not very easy to choose the characteristic value, which one we should use. Mean, generally we choose the mean, but obviously lower bound is not suitable. Upper bound is over-designed. So generally the seabed property, soil property is not homogeneous or just very simply linear increasing with the depth. So in this presentation, I'm going to show that how to incorporate the soil spatial variability into the prediction. And so I have to introduce uncertainty. Uncertainty is a state of limited knowledge. It's not just about the seabed state. It's also about the measurement errors. Everything like the prediction of the equation also involves some errors. All of those uncertainties. So in this presentation, I will just incorporate the seabed, the inherited spatial variability, but not the prediction errors. So if you want to incorporate the spatial variability, how? Here I'm going to use the random field theory, which is quite simple. We can only simulate a stationary random field, which means that the mean standard deviation or the correlation structure at every point, all of the points in the soil mass is the same. So it's defined by three parameters. One is mean, the standard deviation, and also the correlation function, which they use to control the autocorrelation structure. That is it's kind of like if we measure something at one point, if the other point is very, very close to the first point, the property will be very, very similar. This is the correlation. So the correlation function they use to control how the property, the soil property at the 2 points, how they are correlated. And mean standard deviation, I think many people are familiar with this. If you have done some distributions. So we need the mean, the standard deviation, or also the distribution tab. We can characterize the random property. So this is a generated random field, two-dimensional. So you can see that at each point, all of the points, the property at each point are different. So how can we incorporate the random field theory? And here we're using the LAS method, local average subdivision. The theory behind it is quite complicated. I just introduce the concept behind it. So it's kind of like the finite element. So we have a very big element, and we divide into 1 to 2, and the mean and standard deviation will follow the same thing we just defined, and the correlation structure will follow the correlation function we defined, and 1 to 2, 2 to 4, and 4 to 8. So we just divide it, and this is one example here, and the second picture is the same example, but we put more elements. You can see that it's like the pixels have more pixels here, and the resolution is higher. And using this method, we can incorporate the spatial variability. And as I said, this is like the element, finite element. So we can just very easily put the random field theory to the traditional finite element methods. So random finite element theory plus finite element methods, we call it RFEM, so RFEM. This is also a kind of Monte Carlo simulation because the soil property is random. So we have to use a Monte Carlo simulation to random it many times and use it and put it into the finite element methods and calculate the results. And in this approach, the pull-out capacity factor NC and N gamma traditionally is deterministic. It's a function of the soil property because the soil property is deterministic. So NC and gamma is also deterministic. But here, we make the soil become random, and the pull-out capacity factor NC and gamma will become random as well. So we use MCM gamma instead. So the task here is to estimate the statistics, like the mean, standard deviation, and also distribution tab of the pull-out capacity factor. So I'm going to put example here. We're going to investigate clay and sand separately, as we always do in practice. So clay is characterized by the end-drainage strength. We assume that it's log normal distribution. The main reason is that end-drainage strength should never be negative. So we use log normal distribution, which is always non-negative. And the sand is characterized by the property friction angle, the phi. We just mentioned that. And the friction angle is a bit different. It's not just a positive. It is positive, but it's also limited to a certain range. Generally, it's 20, and it never exceeds 45. So it's limited to 20 to 45. So we use the bounded the tangent distribution. It has a lower bound and upper bound. And we can also, the mean, we can just keep the mean, like the SU for the end-drainage strength, the mean is 30 kilopascal. And the coefficient variation, which is the ratio of the standard deviation to the mean value, we change the value. Like for end-drainage strength is normally between 0.2 to 0.5, and for the friction angle is 0.05 to 0.15. So this is the distribution. And so we know the mean, we know the mean, we know the standard deviation, and also distribution tab. And the last thing about soil parameter is the correlation function we just said. So how they property at 2 points, how they correlate with each other. We use the Markovian correlation function, which is exponential decreasing, which means that when the 2 points are very close to each other, their property will be very, very similar. And when the distance is getting bigger, they will be very different. And when the distance is infinity, it means that they are independent. So we use a Markovian correlation function, exponentially decreasing. This is a random finite element here. So before we conduct the RFEM, we should validate the numerical model. So we need to use the homogeneous result to validate that. So first, we just use homogeneous. We don't consider the spatial variability. We just use homogeneous results. And we compared with the published results, like the top one. The top right is NC. You can see the pull-out capacity NC here. And compares very well with the previous FEM and also analytical results. And you can see here that it reached to a plateau. This is a deeply embedded case. When the plate anchor is embedded deeper and deeper, it reaches to some critical points. The pull-out capacity won't increase anymore. So you can see it here. This is for clay. And for sand, it's the same. We also compared with the published results, lower bound, upper bound, and also limit equilibrium results. They all compare very well. The graph on the left is a random soil, and you can see the contour here. The light and dark area means that the soil property are different. Dark means soil strength is bigger. And in the finite elements, we just pull out the anchor. This is the anchor, which is the rigid. We assume the rigid because it generally is a steel, which is very, very rigid compared to the soil. So we assume the rigid, and then we pull out the anchor, and we can, in the finite element code, we can find out the pull-out capacity, the relationship between the pull-out capacity, but pull-out pressure and also displacement. Then we can find out the maximum value. So this is the RFEM, this example of deformation. And as I said, this is the Monte Carlo simulation. We have to do many times. And in this case, we just choose 2000 realizations, which means we have to use the RFEM codes to repeat 2000 times. It takes quite a lot of time. How can we verify that? So we just find out the sample mean, like the MC and M gamma, find the mean and standard deviation of them for different cases. And we can see that it gradually becomes stable. And at 2000, actually, it's very, very stable. So 2000 realizations are sufficient for this case. And those are some results. Who's the mean and standard deviation? This is the first column is the mean, the second column is standard deviation, and the first row is the clay, and second row is the sand. I just put one coefficient variation for clay is 0.3, which is the intermediate value. For phi, the same intermediate value 0.1. And you can see that the mean value of the pull-out capacity for clay, for both clay and sand, it doesn't really affect. Now, I have to mention that horizontal axis is normalized correlation length. Correlation length is a parameter in the correlation function, which is used to measure the correlation structure, how closely the property 2 points they are. So the correlation length doesn't really has a very, very minor effect on the mean value, but for the standard deviation, you can see that when theta value is very, very small, approaching 0, the sigma of MC or M gamma also approaches 0, and it also reaches plateaus for different embedments. H is the embedment depth, and B is the width of the anchor. So the ratio is the embedment ratio. I just put 4, 1, 2, 4. And you can see that
Pengpeng, I'm just going to let you know, just got about a minute left, if that's okay.
Okay. So we're running out of time. So the second one is about I just keep the embedment ratio the same and change the coefficient variation. They have the same pattern. And for the mean value, it's the same. It doesn't really affect much. And so the coefficient of variation of the Pullout capacity factor, which is the ratio of the mean to the standard deviation to the mean, you can see that this is for sand, this is for clay, this is for sand. And H over B, the 1, 2, 3 is shallowly embedded. This is deeply embedded. And once we know the mean standard deviation, we should also find out the distribution of the MC and M gamma. You can see that it follows closely log normal distribution. So once we know the mean standard deviation and also the distribution tab, we can use the probabilistic analysis. I won't show the theory here, just put the result here. So this is the probabilistic design charts for clean sand. Once you know the PM is a target field probability, once you know the target P, and you know the theta, which can be found out from offshore set investigation, and then you can find the factor of safety, which is the global factor of safety. See the for clay, this is for sand. See the traditional methods, global factor of safety, we can also use it to calibrate the currently used load and resistance factor design, which is encoded in the European Code 7. So I think that's it. And all of the results come from our recently published 2 papers on the Journal of Geotechnical and Geoenvironmental Engineering, part 1 and part 2. Just accept it. Takes us some time to be online. If you want to get more information, you can refer to the papers probably later. And I'm going to conclude my presentation by this: uncertainty is a key, and always make room for it, not just for geotech. For I think for all of the engineering disciplines, we should consider uncertainty at some point. And again, this is my research interest: offshore geotech, probability analysis, and machine learning in geotech. If you're interested, you can just email me, and you can find my personal page, Google Scholar, GitHub again from the QR code. I think that's me. Thank you.
Okay, thank you very much, Pengpeng. That's a really interesting presentation, and yeah, very nice to see those results. And also, I like your final statement there about uncertainty. Agree with you absolutely.
Thank you.
Unfortunately, we have really got to the end of our time, and I'm sure other people have. Well, we need to close really at 2 o'clock. So there is a question from Xinyu Wang, but I will ask if you could follow up with him, perhaps by email afterwards. It's a question about using plates for TLP in design, for TLP mooring designs. But if you have a look at that, that would be great. I'm going to ask Kirsty to put up the slide she has to advertise the masterclasses, because I would like to remind everybody that we're offering a series of masterclasses. And they're free for research ECR researchers to attend, if you can get yourself to them. And they go across a whole range of different subject areas. I encourage you to attend as many as you can outside of your area, as well as inside of your area, and they will be a great opportunity to get to know others as well, and to extend your knowledge of offshore renewable energy. So thank you. These are the next ones in Warwick, in real-time hardware in the loop experiments, and that's on the 4th of September. And then we have one in Manchester coming up in October, and in Aberdeen in November, and so on. Please do remember to keep signed up to our website, to our newsletter through the website, to find out more about what's going on. There is a link to a feedback survey in the chat. Be very grateful for any feedback on the webinar series, and should also let you know that the next webinar is scheduled for September, so look out for more details of that. And that will be organised by Professor Tim Stallard at Manchester. So it's likely to be around offshore wind. Okay. Thank you very much. Thank you especially to our speakers. Really interesting talks today. And thank you very much for that, and look forward to meeting you in person at our next events. But I should just say thank you very much to everyone for attending, and look forward to seeing you next time. Thank you very much. Bye-bye.